So yesterday we talked about one form of speech recognition of not just one vowel but a sequence of speech sounds that makes up a word, isolated word recognition. With that we follow the template matching approach, where during training phase a word is spoken, some features are extracted such as MFCCs. So for each speech frame we have a vector of 39-dimensional MFCC feature vectors, and we stored a sequence of feature vectors of length capital M for a given word. We did it for several words, and so we have reference templates for several words, let's say 10 digits. And when somebody else speaks a test speech, the similar features are extracted from the test speech. Let us consider the length of the test speech feature vector sequence as capital N. Capital N and capital M need not be same, because this word and the reference word may be different, or even if they are same, the speaking rates may be different. So we have to take into account the speaking rate variation, and so we looked at the dynamic programming approach, which would find the best alignment between the reference feature vector sequence and the test feature vector sequence. The alignment path will start from the 1,1 grid point and ends at capital N, capital M grid point at this point. And we use the recursion, and we stored the results of partial computation in a capital D of N, M, and the small d of N, M represents the distance, squared Euclidean distance or Euclidean distance or any other distance measure between nth test frame feature vector and mth reference vector, that we store here. And we resorted to this recursion to compute the partial equilibrated cost of the optimal partial path ending at N, M, using the cost of optimal paths ending at previous grid points, either to the left or to below the current grid point. And doing this, we could find the best path sequence. What now we will do is to switch over from dynamic time warping, that is recognizing a given phrase, to the hidden Markov model approach, where you can recognize unlimited sequence of words. In dynamic time warping, the word or the phrase, if there is a phrase such as Mera Bharat Mahan, you cannot say Mera Mahan Bharat, it will not be recognized, because dynamic time warping is a template based matching. The sound sequences are prefixed in the template, whereas hidden Markov model permits any combination of word sequences, and so it is used for recognizing continuous speech. So we will talk about this similarity between, in this slide we will talk about the similarity between dynamic time warping and the hidden Markov model as far as the decoding is concerned, as far as the recognition is concerned, recognition of test speech is concerned. In both cases, the test speech is short time processing of test speech leads to a sequence of feature vectors x1, x2, x3 up to x capital N. In the case of dynamic time warping, we follow the reference template approach. Each phrase or a word consists of the feature vectors R1, R2, R3 up to R capital M. And we use the dynamic programming technique to find the best alignment between the test speech and a given reference feature vector sequence of one word in the vocabulary. Now, but firstly, we saw yesterday that the paths need not be necessarily diagonal, it can be off diagonal because of the speaking rate variation even within a word and by the same person and so on. Secondly, since the number of, so if you know the boundary between phonemes, for example, the number of feature vectors belonging to a given phoneme, given speech sound, can vary depending on the speaking rate. And even if the speaking rate is same, the feature vectors can differ because of the mood of the speaker. So there is inherent variation in this speech production mechanism. Whenever there are variations in generation of data, it is good to resort to probabilistic models. Yesterday we did talk about probabilistic models, that is representing the data points of a given class by a normal distribution. Normal distribution is parameterized by the mean vector mu and the covariance matrix capital sigma. Now we will go one step further and use the Hidden Markov Model technology, which represents a sequence of such phonemes as, in some sense, a sequence of probability distributions. So there are such phonemes. Okay. So the difference between the DTW template-based approach and HMM, essential difference is the following: that you consider, let's say there are three phonemes, there are several phonemes, or the symbols. That's why we have the S here. S stands for symbol. So let us say that a sentence consists of a sequence of symbols. The Mera Bharat Mahan consists of somewhere around 15 phonemes. S1, S2, S3 up to S15. Let's say in this particular case there are capital L symbols, and this is represented by capital M feature vector sequence in the reference template. What we can do is to, and suppose now this is a reference template, therefore we recorded it, we can look at using a PRAT or a wave surfer, you can look at the waveform spectrogram and find out the boundary between successive phonemes. So let us say the boundary between the first phoneme and second phoneme is here. So which means that the first phoneme first symbol S1 corresponds to 3 speech frames. They are characterized by the 3 reference feature vectors R1, R2, R3. Similarly, let us assume that the second feature vector, the second symbol S2 is of 2 frames duration, 20 millisecond long. That is characterized by 2 feature vectors R4 and R5. R stands for reference. Now when such thing happen, what we can do is to, instead of representing this particular phoneme by a sequence of 3 vectors, we can represent it by a probability distribution. Let us say, let us represent it by a normal distribution. Normal distribution is characterized by the mean vector mu and the covariance matrix capital sigma. How do you compute the mean? So you need to compute the mean of 3 vectors. That will give you the mu vector. Similarly, you can compute the covariance matrix of 39-dimensional 3. There are 3 such 39-dimensional vectors. You can estimate the covariance matrix. Now we call this collection some unit, linguistic unit, or a statistical model that is generated from the collection of 3 reference feature vectors belong to the first S1 as a state in Hidden Markov model terminology. This is a jargon. It's a state. To begin with, you can think of it, each phoneme being represented by one state, and each state is associated with a probability distribution that characterizes that represents the characteristic of the feature vectors associated with that symbol. So different phonemes, this is the phoneme number 1, and this is the phoneme number 2, and it may have the another let's say sigma 2. So another probability distribution associated with the symbol 2, and these characteristics would be different because these 2 symbols can be different. Okay. So, but apart from that, once you make such model that instead of using a reference template or consisting of R1, R2 feature vectors R1, R2, R3 all the way up to capital M, we now represent the utterance by a sequence of states. In state typically consists of several feature vectors. Now such a sequence of states is called a Markov model. There is a property called hidden Markov model. We will come to that. But apart from that, once you train such a hidden Markov model, recognizing a test speech which is characterized by a test feature vector sequence x1, x2, xn up to capital Xn is exactly same. We found what we do is earlier in DTW we used to match each feature vector with each test feature vector, let's say xn, with all the reference feature vectors r1, r2, r3 up to r capital N. Now instead of comparing this feature vector with all the feature vector reference feature vectors, we find the likelihood of this test data xn. It's a likelihood of xn belonging to a particular state. How many states are there? There are as many states as the number of symbols here. So the number of states is capital L, which is capital L is less than, typically much less than the number of the length of the sequence, reference feature vector sequence capital M. So we need to compute less now, because each test vector xn needs to be needs to be compared with the capital L states or the capital L probability distribution, in contrast to in DTW where we used to compare it with the capital M reference feature vectors. So firstly it reduces computation, but that is a secondary issue. But more important issue is that these states represent variations in the acoustic characteristics of the different sounds using a statistical model. That's the advantage. With that broad introduction, now let us go to see why spectrogram, why hidden Markov model is a good model for comparing sequences such as the speech, which is essentially a sequence of speech sounds. To do that, this is my favorite spectrogram. This sound was spoken by one of my colleagues, and his pitch was low, and he spoke clearly. It illustrates certain principles. Illustrates several principles that are important in speech recognition. So this is a spectrogram of the word Thiruvananthapuram. There's a waveform here, time waveform, time along the x-axis. Here also time along the x-axis is almost up to 0.85 seconds long. And frequency is along the y-axis, and the intensity is shown by color code. So you can see the formants here. Formants are high energy regions, and formants are shown in red color. So this is the sequence of sounds are written here. You can see the up to here is ta, and up to here is E, this strip, R, this low energy strip, and you can see here are U, and so on, all the way up to Puram. Okay. Now, if this part I talked earlier also, but I'll re-emphasize. Let us consider this is one word spoken by one person. Let us consider two repetitions of the vowel U. U occurs here in Thiru, and U occurs also in Puram. Now the U here, so these are the U parts here as well as here as far as the waveform concerned. They appear similar, but it is difficult to distinguish different vowels in the time waveform. So let us consider the frequency domain. Let's look at how the spectrum varies as a function of time. So if I approximately plot the boundary of U, this is the boundary of U in the spectrogram, and let us put the boundary of U in the spectrogram, the second token or second utterance of the U in the same word. Now what I will do is to compare the formant frequency behavior as a function of time. It's called formant frequency trajectory. Trajectory is how it varies with respect to something, in this particular with respect to time. What you see here is that in this particular case, the Formant frequency is decreasing. Okay? It's going from high value to the low value in anticipation of a bilabial sound wa. Bilabial means wa is involved in the production of the production of wa involves lips, so the Formant frequencies are low. Second Formant frequency is low. I'm right now looking at the second Formant frequency. Now consider the same vowel oo, the same word spoken by the same person at the same time. The Formant frequency seems to be increasing. What we expect is that the one vowel should have the same characteristic. Let's make 2 points. One, firstly, the characteristic of vowel oo we expect it to be constant during this duration. It isn't, it is varying. It's a time varying characteristic. Secondly, the time variation of the vowel can be, sometimes can be positive, decreasing, sometimes it can be increasing. So there is variation in the time characteristic of the different sounds, but there is some method in this madness. There is this variation is systematic. It is predictable if we know the identity of the adjacent sounds. Of course, in speech recognition we don't know the identity of the sounds, but during at least training we know which sound occurs before the oo and which sound occurs after the. Before the oo occurs r and oo is followed by w. Quite often the characteristic of the vowel is influenced more by the following sound w than the preceding sound or the sound that occurs earlier. Now what has happened here is in oo is followed by vowel w whose Formant frequency is low. So the typical Formant frequency of oo is here, and typical Formant frequency of w is lower. But when you are speaking, the articulators move slowly. They cannot take stepwise jump. They move continuously. Therefore, even when the person is speaking oo, his lips are moving, is elongated towards the position of w. Therefore, even within the vowel oo, the Formant is changing in anticipation of the following sound w, following bilabial sound w. On the other hand, here if the situation is ulta, that the expected value of the F2 of the oo is here. That is true. But it is preceded by a bilabial sound p. P and wa both involve lips, therefore their Formant frequencies are lower. So when the person spoke pa, Formant frequency is lower, and so he has to go to the target Formant frequency here, but the Formant frequency is increasing. So therefore the characteristic of a Formant characteristic or spectral characteristic of a sound depends not only on the sound which follows it, but also on the sound which precedes it, which occurs before that. This effect is called phonetic context. So let me write it here just to be on the, so that this effect, phonetic context, that means it depends upon which phone sounds come before and after, and the trajectory of phonemes for a given vowel depends on that. What I will now do is concentrate. I want to move on to the HMM. I want to motivate or illustrate why Hidden Markov Model, which is a Markov model, which is a sequence of states, is a good model for speech recognition. To do that, I will concentrate on this sound a. Okay? This particular sound a, vowel a, which is boundary between this and this. So let me concentrate on that. So ignore this. Let's concentrate on that particular part. Now if you look at this a, again a occurs here as well as here. Its behavior is different. Here F2 is increasing, here F2 is constant, and at the end F2 is constant for a while, and at the end it suddenly drops. Why does it drop suddenly? Because it is anticipating another bilabial sound ma, whose Formant frequency is low. So the Formant frequency characteristic is constant and drops here. This is the characteristic of the third Formant frequency, that is F2. Sorry, second Formant frequency, this is F2. F1 is here, F1 is increasing like this. Let us look at the F3. F3 is here, it increases and remains constant. Now let us look at the F4. F4 is here, it is decreasing slightly and increasing. Let us look at F5. If you look at the F5, it increases slightly and decreases slightly. You see, within a sound, different resonance frequencies, different Formant frequencies vary differently. That depends upon the Formant frequencies of the previous sound and the following sound. But something that you can sort of notice here, that the middle, this particular Formant frequency that I drew earlier seems to be sort of constant in the middle part. If you look at this middle part, this is constant, 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 constant. What happens is the left part of the Formant trajectory, how it behaves with the time, is influenced by the previous sound R. The right part of the behavior of the vowel A is influenced by the following sound M. Therefore, you can think of this vowel A as consisting of three parts. What I have done is, whatever I drew by hand on the previous slide, I have drawn it here specifically, typical behavior. So the second Formant frequency is nearly constant and drops down. This is the third Formant frequency, increases and steady. Fourth Formant frequency is like this, fifth Formant frequency is like this. So you can see that the trajectory of the Formant, as shown by red lines here, of the vowel A can be seen as consisting of three parts. The middle part, which is generally the characteristic of that particular vowel, the middle part, which is reasonably constant, which is reasonably steady, hardly any variation, very little, let me say, very little small variation as a function of time. Whereas the left part, which varies, one Formant can decrease, another Formant can increase, this is influenced by the preceding vowel. And the right part is influenced by the following vowel. Okay? Therefore, it is better to represent one phoneme, one speech sound, as a sequence of three states, as a sequence of three segments. And each segment and within each segment also there are variations. Therefore, what we will do is, we will represent this phoneme as a sequence of three segments, and each of the segment is represented by one probability distribution. Let me call this first probability distribution of the first part as a normal distribution, but mean vector mu1 and covariance vector sigma 1. And the middle part also as, let's say, n of mu2, the middle part, it's also a mean vector, and the covariance matrix is denoted by sigma 2. And by the third one, which let us denote it by mu3, the mean vector of the third part, and the sigma 3 covariance matrix. So what is better? But this graph illustrates that it is better to represent one phoneme as a sequence of three segments. It's a sequence, time ordered, not a set, sequence of three segments, and each segment associated with one probability distribution. Okay? So now let us say, earlier in DTW, what we had is sequence of feature vectors 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 or something. Okay? So probably there were 5 feature vectors here, 3 feature vectors here, and 3 feature vectors here. When you did a DTW of a word Thiruvananthapuram, the vowel A, the length of the vowel A was 11 frames, and and this is how the sort of you can split it up into three parts. So now the vowel A in the word Tirunantapuram, vowel A in the word Tirunantapuram is represented in DTW as a sequence of 11 feature vectors, 3 plus 5 plus 3. On the other hand, in HMM, Hidden Markov Model, that we are going to talk, Markov Model, we represent it as state 1, a sequence of 3 states, state 2 and state 3. So, in DTW, we represent it as represent the one vowel as a sequence of several vectors, whereas in Markov model, we represent the same vowel as a sequence of 3 states. These are called states. The segments are called states. Subphonetic segments are called states, and each state is associated with the probability distribution. Now, how do you find out, estimate the parameters of this probability distribution? If you know the boundaries, then between these 3 parts, we can take these 3 feature vectors, find mu, mean vector mu, and covariance matrix sigma. Now we have a model for the first state. We have estimated the parameters of the normal distribution associated with the state 1. You can do the same thing for the state 2, and you can do the same thing for the state 3 using 3 here, whereas the middle state parameters are estimated using 5 feature vectors. So that is the genesis or the motivation for Hidden Markov Model, that a vowel is best described as a sequence of states rather than sequence of feature vectors in DTW. Now we'll come to the sort of graphical description of these state sequences, the kind of graph that you see in Hidden Markov Model tutorials. So this is called actually a Markov model. Markov model is a sequence of states. That is, if we ignore the probability distributions of the sequence of states, then it is called a Markov model. On the other hand, if there are probability distributions associated with the states such that the characteristic of this particular state, what you can see, what you can observe, the Formant frequencies or MFCC coefficients that are associated with this, if it is not deterministic, if it doesn't change, if it changes with the time, changes from one repetition to another, then we associate the probability distribution. Such a chain of Markov models is called Hidden Markov model. So the Hidden Markov model of this vowel A is represented a sequence of 3 states. Each state is associated with the probability distribution, as we saw here. And now, what are the parameters of this Hidden Markov model, which represents every sound as a sequence of states? Firstly, there are 3 probability distributions. So each probability distribution is associated with the parameters. So typical terminology that is used in HMM technology is that this state is the probability distribution associated with the state 1. State 1, this is the probability distribution. It is denoted as B1.